So I wanted to do a quick video on the horizon. This is the view from the cockpit of a Robinson R-22 helicopter, which I actually have a license for. This instrument here is the magnetic compass, and it's sighted up this column away from the instrument panel down here, because the instrument panel is full of gyroscopes and electronics. It interferes with the magnetic compass, so they move it up here out the way to eliminate that interference, and in doing so it provides a convenient visual reference for the pilot to use as his attitude indicator, if you like. It enables him to keep the aircraft at a steady attitude, a cruising attitude, and it makes the aircraft more efficient. So he simply uses the stick here, the stick, to align or to lift the nose of the helicopter up or down to keep this magnetic compass aligned with the horizon, as you can see this guy's doing here. One of the other things that we used to practice was we would hover at any altitude. It could be 1,000 feet or it could be at 10 feet, and we would get this compass on the horizon and we will practice a spot turn, which is using the pedals to turn yourself on the spot, and the idea being you do it perfectly straight and level, and the way you do it is to keep this compass on the horizon at all times, and if you feel yourself deviating from the horizon, you compensate either with the cyclic stick or the pedals or whatever, or even the collective lever. The horizon was always completely flat. We relied on it being completely flat to be able to perform the manoeuvre straight and level. I never saw any indication that the horizon was curved in any way, as that would have hindered this manoeuvre. Anyway, on to AutoCAD. This software is extremely powerful and it's extremely accurate. One thing to note is that if you draw a circle in AutoCAD, it renders it as a series of continually rotating straight lines until you do a regen. And the reason it does this is so that it can, the graphics card can display the image quicker without having to do things perfect. But to overcome that, all you need to do is type REA, which stands for regen all, and it makes the circle perfect again at that particular magnification until you move or pan. I'll explain why that's important later. The other thing to note is that it does all the work for me. It eliminates human error. So if I wanted to draw a line from the quadrant point here, which is the 270 degree position, all I need to do is hover over the circle somewhere and it automatically snaps, look, to the quadrant point there. So if I click there, put my orthographic on, and if I drag the cursor to the left and type 100, it will draw a line 100 miles in the 270 degree direction. Then if I wanted to join this line to the circle tangent, all I need to do is type in the word tan, hover over the circle, and it puts that green symbol there, look, at the tangential point. It eliminates any human error. It's done all the work for me. I haven't had to do any maths. Okay, so if I zoom into the top of the globe, where I've already drawn a line 6 miles vertically upwards from, let's call it, North Pole. If we look over here, look, the length of this is 6 miles. It's telling us it's a line and it's 6 miles long and it's 90 degrees from the horizontal. Incidentally, what I didn't show is if I select the circle itself and display the properties for it, it tells me here, look, it's a circle, it's blue. It tells me the radius, the diameter and the circumference, and as you can see, these figures here are the generally accepted dimensions of the globe. So everything's drawn to scale, perfectly to scale. Let me zoom back in. There's the 6 mile high line. If I zoom into the top of it, I've already imported the model of a Boeing 747 exactly to scale. And I've drawn a line from the passenger window, the red line here, and I've drawn it to the tangent point on the Earth. Now, you remember I said earlier that that AutoCAD won't render a circle, it'll do it as a series of straight lines. It's done it here, look. So if I type that command REA, it'll bring it to a perfect circle again. And you can see that the line here, which is the line of sight from the passenger on the plane to the horizon, it touches the circle precisely. I then drew a line back from this point horizontally to underneath the aircraft, just here. And you can see that the distance now from the horizon to the aeroplane is 11.99 miles, which is almost double the altitude of the plane above the Earth. And it conveniently actually works as double around this sort of altitude, around the 6 mile high altitude. The distance to the horizon works out to double. If you start going higher and put lines in 100 miles high and do the same exercise, it gets to slightly less than half. For instance, if I did it at 100 miles, it would be what would it be? Be about 197 miles, I think, something like that. Anyway, so it seems to conveniently work as double around this sort of altitude. So let's have a look at what this looks like from the perspective of somebody on the plane. So here, again, I've drawn the aircraft exactly to scale. Down here is the height they are above the Earth, 6 miles. So this is directly below them. And then this is the horizon, which is a further 6 miles, giving the total of 12 miles. 12 miles. So let's have a look at the artificial horizon in the aircraft. The passengers on the plane don't experience any nose up or nose down attitude of the plane. The instrument tells them they're flying straight and level. For all intents and purposes they are. However, the horizon is 12 miles below them. What would they need to do in order to correct it? They would need to nose down, but the instrument is reading straight and level. Doesn't work. And this is not what we see. We don't see the horizon 12 miles below us. Let's have a look at the flat Earth model. Same position, just here from the North Pole. This green line here depicts the flat Earth, and I've drawn it at about double the diameter of the globe here. So it's the same aeroplane, same height, 6 miles. This time we've drawn a line out of the window this way, right to the end of the flat Earth, wherever that may be. This is kind of the minimum distance for it, based on the commonly accepted flat Earth models. And we see that the angle from the horizontal, which is the white line here, to the angle that it is to the flat Earth horizon is 0.04 degrees. It's next to nothing. For all intents and purposes, even at the sort of smallest possible flat Earth, the horizon is at eye level. Of course, if this was an infinite plane, then the angle would be approaching zero infinitely. One of the figures I forgot to mention is this: in the globe model, the distance from the aircraft at 6 miles cruising altitude to the horizon is this red line here, which is selected. So if I go to the properties of it, it's 218 miles. So that's the distance to the horizon at 6 miles altitude, and that gives you an angle from the horizontal of 3.15 degrees. Still doesn't sound a lot, but over 218 miles it gives you almost 12 miles of drop. So let's just quickly wrap this up and have a look at what we actually see. Here's the aeroplane. The passengers on the aeroplane, out of both windows, they see the horizon at eye level. The instrument's reading eye level. The horizon is as it should be. All passengers are experiencing straight and level flight. It all works. Okay, the last thing I wanted to show was what would happen with helicopters if they were to ascend vertically into a hover at various different altitudes. So I've drawn the helicopters here at a massively increased scale. The globe here is still to scale, but I've increased the scale of these helicopters quite significantly so that you can see them. The first one is at 6 miles altitude, then 100 miles, and then 200 miles. And I know that helicopters don't usually fly at that altitude, but the dynamics at play here would be the same regardless. So this is the 6 mile altitude here as viewed by the pilot in the cockpit, and this is the same angle and the same length as in the previous example with the airliner. Now, one thing to note is that the helicopter has been tilted here to align with the horizon here. Now, if you're in a helicopter, the only way to tilt your nose down is to push forward on the stick, on the cyclic stick. But in doing so, it tilts the rotor disc downwards at the front and causes you to move forward. That's how you transition from a hover into forward movement, fast forward flight. You push the stick forward and the nose dips and you start moving forward. There are other things you need to do as well, but that's essentially what happens. So let's see what would happen if we was to ascend to 100 miles. Well, we would, in order to keep the horizon at eye level, we would need to really push the nose of the aircraft down. So this meets the globe at the horizon here. Again, it was drawn in AutoCAD. It is precise, and you can see it forms a 90-degree angle perpendicular to the centre of the circle. And then if we go to 200 miles, it becomes insane. Look at the angle that the helicopter would have to be to keep the horizon at eye level and hover. It just wouldn't work. It can't work. The more and more I look at this globe model, the more and more it goes from being a lie to just ridiculousness, absurdity. I mean, how can you account for this? The way to hover is to keep the horizon at eye level. If I keep the horizon at eye level at this altitude, then we're at all kinds of funny angles. Even at 6 miles high, that attitude, that angle that the helicopter's at there, could only be achieved by pushing the stick forward, which would cause you to move forward into fast forward flight. Just doesn't work. Thanks for watching, folks.